I don't think you can know, but I know it's like super easy.
Yeah, I think they have to like send it.
Yeah. It's funny because the frats are so different. I have friends in AU and they're like, yeah, you can come live with us. Like, go to
So tomorrow, do you want to meet up and see
Yeah. I'm gonna do, I haven't done just practice yet.
and
I started this student, but they come on. I think it's gonna be
Okay, I need to sit down for a minute. Nope, I started a new stream. I'm just gonna let people find me for a few minutes. We can take a break. How's life? Life's good. I don't know, this whole E thing has been weird. What's my workout routine? Like I said, now it's going to be a lot of pull-ups and a lot of push-ups because I don't have much choice. I'll run a lot. Board is very blurry. Did that change it? What makes me choose UCLA for graduate school? Okay. Well, UCLA's got a really strong math program. It's like a top 10 math program. It was the best place I got into. So, and it was like UCLA. I'm not going to say no to that. I went to Northwestern for undergrad. I did. I love Northwestern. What else was there? Plans for the future. More of this, hopefully. I just want to teach people math. Yeah. Shy, could you pass me some gummies? 2. I'll probably be here for 2 more years. Yeah. Probably 2 more years.
Yeah, at the same time. We haven't gotten any.
We'll get it this time. Oh, so close. What level of math do I want to teach? I want to teach calculus, like 31B, 32A, 32B. That's my favorite stuff to teach. Okay, I'll eat my 2 packages of gummies. I'll answer questions until then, and then we'll get back to the math. Nice. I TA'd for 115A honors one time, and it was fun. I just like calculus more. So, but like I said, I really don't know what my teaching is going to look like the next couple of years. It'll be kind of up in the air. So maybe.
Do you start TAing your first year of undergrad?
Or first year as a grad student. Yeah. I admire what they're fighting for because it is hard to live on a grad student stipend. To be completely honest, I don't know much about the details of the whole scenario, but I could be completely wrong, so don't hold me to this, but I feel like I remember reading that they were demanding like a pretty insanely high increase in pay, which like I get, like I wouldn't mind that, but it seemed quite extreme. So I don't know. Yeah, if you guys, well, I mean, next quarter I'll just be doing online review sessions again. So if you want to tune in to watch me eat gummies, then feel free to do so. Oh yeah, like a 70% pay raise. Yeah. That seems a little too ambitious to me. Maybe unrealistic. I don't really know though. Okay. Almost done. Yeah, me too.
What if Dimitri is still teaching? I heard
Well,
he's like not even really a
No.
professor.
Yeah, he usually only teaches in the fall.
Oh, really?
Yeah, he's um I don't know how much you know about him.
Someone told me that he like, well, I know he lives in San Diego, which is crazy. And
Yeah.
someone said he's like really rich, like,
Yep.
and that he doesn't like take money when he pays.
Right. Yeah, he donates his salary. He's donated a lot of money to
Is that why?
the math
I'm not gonna
department.
make assumptions about why why he teaches.
Yes.
Have you TA'd me before?
No, that was the first time last quarter. All right. Oh. Okay, I'm ready. Tea time's over. What were we doing? I don't even remember. We were finding critical points. And I think I froze when I broke this down into two scenarios. One of those scenarios was when x was 0. And when x was 0, oh, chalk's over here. When x was 0, the first equation turned into something like this, and there are no solutions, so we don't get any points here. Okay, so then I consider this scenario, which tells me that x is 2y. And probably what I would do is I would plug that into this first equation, and then I have a scenario, or then I have an equation only involving y, and I can hopefully hopefully solve for y. So plugging this into the first equation turns into 2x is 4y, so I get 4y squared minus y squared minus 3 equals 0. So this is 3y squared minus 3. So I think 3y squared should be 3, which means y squared is 1. So this gives us two values for y, plus and minus 1. Using these two values for y, and then using this, I can generate the corresponding points. Okay, so when y is negative 1, when y is 1, what's the x value? It'll be 2. And when y is negative 1, the x value is negative 2. Check the chat. Are we still gossiping? Yes, we are. So Jacob Rooney is my academic older brother. He got his PhD here a couple years ago from the same advisor that I have now. So I'm like a mini Jacob in training. Okay, we've got more lag. Damn. I guess I'll keep going. We found the critical points. Now we just have to classify them. Here's what the second derivative test says. It says, when you find your critical point, compute the determinant of the matrix of second derivatives. What does that mean? That's going to be the determinant of the matrix where I put an xx derivative here, a yy derivative here, and then the mixed partials, which are going to be the same on the off diagonal. So that is to say that the number we want to compute is fxx, whoops, times fyy minus fxy squared. Okay, so I compute this number. I am noticing you. Okay. Oh. I lost my train of thought again. Oh, right. I was talking about the second derivative test. So you compute this determinant, and then there are three scenarios. And I may not be able to fit them all here. But the first scenario is that this number is positive. Now, if this determinant is positive, there are two sub-scenarios, right? Either this corner is positive. So if the determinant's positive and the top and the xx derivative is positive, that's what gets you a minimum. The other possibility is that this determinant is positive, but the xx derivative is negative. That gets you a maximum. That's one scenario. The other scenario is if the determinant is negative, you get a saddle point. And then lastly, if the determinant is 0, who knows? You got to do something else. The test is inconclusive. Excuse me. Okay, so that mess is the second derivative test for two variable functions. And that's what we're going to do to classify each of these.
Did we learn what else to do?
So if you get 0, what do you do? Really the thing to do is to look at traces. You kind of just have to like think about how the function behaves, but in general, I would chop through and look at traces to see if it looks like this or something like that. That's kind of what you have to do, unfortunately. All right, so let's do that here and hope it works. So first of all, we can compute this matrix of second derivatives. So the determinant as a function of x and y is going to be, damn, I erased the first derivatives. So that'll be annoying. Thanks. What was the x derivative? I guess I could. Probably not so hard to compute. The y derivative was x squared minus 2xy. Okay, so the xx derivative is going to be the x derivative of this, which is 2y. Down here in this corner, this is going to be the y derivative of this is negative 2x. And then it'll be the same upstairs, 2x minus 2y. Okay. That's the determinant matrix, or that's the matrix as a function. To check each of these points, we can pick one of them, plug them in here, and then do this stuff. So first I'll consider the point 2, 1. D of that point, D of 2, 1, is going to be, this will be 2, this will be negative 2, this will be 4 minus 2 is 2, and this will be the same.
Is the bottom right? That's beautiful.
Oh, thanks. Good catch. It should be negative 4. So, we good now? I think so. Okay, and so what is this determinant? It'll be negative 8 minus 4 is negative 12. Okay, so we got a negative number here, which means this is a saddle point. So by the second derivative test, 2, 1 is a saddle point. Then we check the other one, and we'll be done. Okay, so the other one was negative 2, negative 1. So next, consider the point negative 2, negative 1. Plug that into D, and we'll get D of negative 2, negative 1 is negative 2, 4, and then 2 times x is negative 4, plus 2 is negative 2, negative 2. This determinant is also going to be negative 8 minus 4, which is negative 12. Okay, so also, it's also a saddle point. So by the second derivative test, this is also a saddle point. Okay, and then after a long break, we are finally done with this problem. Would I recommend plugging in points and solving for the second derivative test equation rather than solving for a general equation? I don't know if I know exactly what that means, but sure. If you mean like, I'm still confused. Sorry, guys. So at some point, you have to compute these things. And there's kind of no way around that. If you want to write it like this, or if you just want to write this, that's fine. I don't know if that's what you're asking about, but if you just like write this, like that's fine too. I just think about it this way, but at some point you do have to compute the functions fxx, fyy, etc. And there's kind of no way around that. I think I'm still misunderstanding. But no matter what you do, like you'll have to find the function fxx, for example. Anyway, that's that problem. Oh, so if you're saying like, okay, like multiply this out. Oh, I'm sorry. Okay, that makes sense. To me, this is the same as this. They're not really any different in my mind, so I think that's why I was getting confused. But yeah, if you want to write out like 2y times negative 2x, da da da, da, and then simplify, you could do that. I think it would be easier to do what I did. Maybe that's what you're pointing out is like I feel like I would screw up or something, but either would work. Yeah, so that would work. To me, same thing. But if you'd rather do that or if you'd rather do this, I think they're fine. I guess I think about it doing this way, but okay. Took a while. Sorry. Nice. Thanks. Nope, it's all good. My bad. Okay. Okay, that was the longest example of all time that it crossed over to two different streams. What do we want to do next? Oh, I know what I want to do. I want to draw a picture. Oh yeah, we could do, I have a curvature problem. I have problems for all of these things. Let me draw a picture first, and then we could do some other problems. I forget to. Okay, here's what I want to do next, and then we'll do other stuff. This will be the kind of thing where I draw the contour plot of a function, and then I'll ask questions about the partial derivatives. I'll ask about the gradient, stuff like that. So let f of xy have the following contour plot. X, Y. I'll draw the contours in blue. Let's do that. I don't know. Then I'll draw some points. P, let's do Q, and then let's do, doesn't matter. R. Oh, and I'll also tell you the values of all these level curves. 1, 2, 3, 4, 5, 6. How about that? If you guys can see, sort of. Okay, and then here's some questions. Where or identify a critical point. And is it a max or a min or a saddle? Then I'll ask about the y derivative at q. Specifically, like, is it positive or negative or whatever? I'll ask about the second derivative, the y derivative at q. And then also draw the gradient of f at r. How about that? Okay. Oh, chain rule. Yeah, thanks. Yeah, we could do that too. We'll see when I get tired. Okay, so where is a critical point? John? P is a critical point. Okay. And it looks like it's a minimum probably. So around it, the level curves are increasing in value. Here, the value of the function's 1. Here, it's 2. So we can suppose by the information that we've been given that, excuse me, P is a minimum. Well, so it's a good question. And as always with this kind of information, you have to just look at a picture and the information's imprecise. But one way to think about it is, if I ignore what else is happening, what do these level curves tell us? They tell us that when you slice through at a height of 3, you get a circle. And then slice through at a height 2, you get a smaller circle. Slice through at a height 1, you get an even smaller circle. And we can kind of assume that as we slice closer and closer and closer and closer, we're going to get smaller and smaller circles, and eventually they'll kind of zoop down to this point at P. So roughly what this picture right here is telling us is that the graph of the function is like the bottom of a bowl or something like that. To be, yeah, that's the idea.
I have a question. Are B and C asking if the y derivative and y derivative are positive or negative?
Yeah.
Okay.
Yeah, I'm asking in B and C, like, are they positive or negative? And I was just too lazy to write that. So, yes, so these are all good answers. It's definitely not a saddle point, because a saddle point behavior is when you have in one direction the function decreases, and then in the other direction the function increases. And if I start at P, no matter what direction I go, the function's going to increase. So that indicates that it's a minimum.
How might a saddle point be represented?
So a saddle point is usually going to look like you'd have a contour kind of like this. Whoops. And so these blue lines are contours, like these are level curves. So usually you'd have something like, let's say this is height 0, 1, 1. This is also height 0, -1, -1. So what this is telling you is that like in this direction, it's a minimum. And in this direction, it's a maximum. But this is kind of the model picture for a saddle point. Whereas here, in all directions, the function's increasing. So the subtle thing is that it doesn't mean that the derivatives are both positive. Like taking derivatives is an infinitesimal quantity. So all the derivatives are 0 there. So the derivatives are 0 here. So the reasoning there is like if I drew if I drew y equals x squared and I went to 0, no matter where you go, the function's increasing. Does that mean that the derivative is positive at 0? Nope, because derivative is an infinitely small thing, and infinitesimally, the function's not increasing at all. So that's the subtlety. So anyway, the derivatives at p would be 0. One way to think about this is that p, the point, that's a level curve. And it's a level curve consisting of a single point. What's the gradient there? Yeah, it'll just be 0. You can think about it. Let's move on. Part B. Oh, I need to write something. P is a critical point. And furthermore, it's a minimum, a local minimum. In part B, at Q, I want to know if Fy is positive or negative. Oops. Oh, did Alonzo ask a question? Oh, yeah, he did. Do I think there will be a lot of conceptual stuff on the final? Honestly, probably not. Just based on the first 2 midterms, they felt pretty computational to me. Like on the first midterm, there was that question about match the final to be the same. If any kind of conceptual stuff comes up, to me, it would be something like this, but I have no clue. All right, what do we think about the y derivative at q? I think it's positive because the y derivative says start here and move north. How does the function change? And we f sub y at q is probably positive because the value of the function probably increases with an infinitely small change northwards. Is that a word? It is now. Northwards. Nice. Okay, so let me try to re-explain. Oh, okay. Well, Abhishek says he asked Jeff, and Jeff said it will be mainly conceptual. So I don't know what that means.
That actually makes sense if it's open book.
Yeah. So what I would do is I would go back to the true-false questions that I wrote on my practice midterms. I have some pretty challenging true-false questions on my website. Of why P is a critical point. I think the real way to think about this, and I'll try to come up with a different explanation. I talked about over here how this was kind of a model picture for a saddle point. A model picture for, say, a minimum is given by the function. Let's just do this actually. Sub problem, and then I'll come back to up here. What if we looked at the function x squared plus y squared? Let's just draw a contour plot of this thing. That'll be a good exercise. So a contour plot, I would look at curves like c equals x squared plus y squared. When c is 1, I would get the unit circle. When c is a half, I would get a smaller circle. When c is a fourth, I would get an even smaller circle yet, etc. And as I make the radius, as I chop closer and closer and closer to 0, I'm going to get smaller and smaller and smaller circles. And eventually they'll juke down to what? What is the level curve at 0, or with height 0? X squared plus y squared equals 0. There's only one point that satisfies that, and it's the origin. So at the origin, the level curve there is just a single point. So when I'm thinking about the model picture of what a minimum looks like, which is exhibited by x squared plus y squared, we know that this represents a minimum. The picture looks like this. Roughly, you chop, so here's the minimum value. You chop closer and closer and closer to the minimum, and you're going to cut out smaller and smaller and smaller circles. I think that's the best way to think about why P is a critical point.
Could that be the definition of a critical point? If the level curve is
it's a good thought, but not quite. You could have critical points that lie on lie on a whole curve.
Oh, yeah.
It's a little weird. Yeah.
But if it is a point, then it is a critical. The other way around, you know? If it is the level, if the level curve is a point.
Technically, no.
Really?
Still, yeah. Oh, okay. Hold on. I need to catch up to. All right. Yep. See ya. Okay. If I have time, which I won't, I could upload explanations to my true-false questions. I have answers, but I don't have explanations. If there's some that you want to talk about tomorrow, maybe we can do that. And then when you have a point on a level curve, and if the function appears to decrease, increase by the same amount in all direction, is it safe to assume that it's a critical point? I think. I think the answer to that question is yes. Okay. Audrey, I don't know if what I said made sense about why P is a critical point, but I think I would keep in mind these local pictures that like a minimum is going to exhibit behavior like this. A saddle point is going to exhibit behavior like this. And the idea is roughly just because of the shape of the graph. It is tricky though. And again, as always, all of these questions are very imprecise because we're just looking at a picture. So there's really no way to know for sure. Okay. Now, to confuse people even more maybe, what about the second derivative, the y derivative at 0? I'm going to sit down now too.
I feel like it's negative because it gets less.
Yeah, so you're identifying the correct thing, which is to look at how far apart the curves are. So, you know, at Q, y is going up, but it's steeper here and less steep up here. So it's steep and then less steep, steep, less steep. Ah, that kind of seems like concave down. Very specifically, the y derivative is more positive here, less positive here. So what is the change in the y derivative as you move north? Decreases. The y derivative goes from more positive to less positive, which is to say that the change in y derivative is negative. So based on my shitty picture, the y derivative at Q is probably negative because f sub y at Q is more positive than f sub y at a point a little north of Q. Things, okay, so for you guys, this is apparently, Jeff already responded to some email that Elijah sent. Quote, things may be a bit more conceptual to compensate for the fact that the exam is open book, open notes, but for most questions, I'll still be asking for a concrete answer.
As opposed to like a proof or something.
Yeah. So f sub x y at Q might be kind of hard. We could try to think about it, but we might not be able to. So f sub x y would be, how does the x derivative change as the y derivative changes? Or sorry, as y changes also. You have to kind of take some faith on the picture here, but I think maybe to identify like the x derivative here at Q, to go up a unit of 1, I have to walk this far. But if I move north a little bit, to say up here, how far do I have to walk to go up 1 unit? I have to walk that far. So that is to say that the x derivative here is larger than the x derivative here. Maybe, it's hard to tell. But so what could be the case is that as you increase y, the x derivative decreases. So I guess I would say f sub xy at Q is probably negative. That one's a little less clear from the picture. Review session. I'd really be into that tomorrow. I probably won't do that, but I'll throw in some more conceptual stuff. Will we be asked to explain? I have no clue. On a question like this, I probably wouldn't ask that because I think explaining it carefully is a little hard. So I probably wouldn't ask for explanation, but who knows?
So
Who
why
knows?
don't we do like hard limits where you have to do squeeze down?
Yeah, sure. We'll do some more limits tomorrow too. Okay, and then the last thing that I wanted to do is draw in the gradient vector at R. The gradient is perpendicular to level curves, and it points in the direction of fastest ascent. So that means it's going to be perpendicular. It will point like that or like that. And the function is increasing this way, so the gradient probably looks like that. That would be part D. Okay. Nice. All right, let's see. I'm getting kind of tired, so I'll do one more example, and then I might call it a night there. Yeah, it's almost my bedtime. Usually 10. Not tonight. This week it's been later with review sessions, but yeah. Usually I'm asleep by 10.
That's so much self-discipline.
Yeah. Or I'm just boring.
Maybe your mornings are poppin'.
Yeah, sometimes. Usually about 6:30 I get up.
Do you still have like grad classes?
Not anymore. I did my first year or two here, but now I don't take any classes. I just teach and do research. Yeah, in college, I was not going to bed at 10, though. It was like 12 to 1 in college. I don't know what I want to do next. Okay, we can compute curvature or find the equation of a plane.
Curvature.
Okay, curvature wins.
But a gentle curvature.
Yeah, it'll be a gentle curvature problem. Let's compute curvature, and then well, let's do both. They'll both be quick. I'll compute curvature, compute a plane, and then eat a gummy or eat some gummies and answer more questions, and then we'll call it a night. Okay. What? Oh. Okay, what next? Thanks. Here's a curve. I want to compute the curvature at some point. So let r of t be the vector t squared plus 1 and 2t cubed minus t. And I want to compute the curvature at the point 2, 1. Okay. Thanks, Audrey. Okay, so now we have to remember how to compute curvature, and the only curvature formula I remember, although you could use whatever you want, especially because it's open book, is that curvature at the time t is given by the magnitude of r prime of t cross r double prime of t over r prime of t, the norm, cubed. That's what I would use, but then I would say, hold on, cross products only defined in 3 dimensions, and this is a 2-dimensional vector. No problem, I can just pretend I'm in 3 dimensions by appending a 0. Whoops, comma 0. And now this formula makes sense. Okay, so then I need r prime, I need r double prime. Let's compute those. R prime of t is going to be 2t 6t squared minus 1 comma 0. But now, what time do I care about? I care about the point 2, 1. And it looks like when t is, I want this to be 2. So I want t to be 1. And then 2 minus 1 checks out. So it looks like the relevant point time we care about is time 1. I just eyeballed it, yeah. So I knew that I wanted to be at the point 2, 1. So I thought, I want this number to be 2. And it looks like t would have to be 1 or negative 1, I guess. But then if t is negative 1 here, then I think we get negative 1, yeah. So therefore, t is 1. There is no cross product equivalent to 2D vectors. There sort of is, but not really. There's something called, right, so if you just pretend that z is constant, now you're in 3 dimensions. So there's nothing that behaves like the cross product in 2 dimensions. Turns out that cross products are only defined in dimensions 3, like 7, and there's like 1 more. It's really weird. Okay. So we actually just care about r prime of 1, which is 2, 5, 0. And r double prime of 1 is 2, 12, 0. Yeah. So then we can plug stuff in here and finish this off. All right, so the curvature that we care about is going to be the norm of the cross product of these 2 vectors over the norm cubed of the first derivative. Oh. All right, so this will be 0 minus 0, 0 minus 0, and then 24 minus 10 is 14. So that's probably the cross product. And then the norm cubed here is going to be 4 plus 25 to the 3 halves. So then I get 14 over 29 to the 3 halves. That would be the curvature. That was a little fast, but you set up these vectors and then you just vomit the formula up and that'll do it. T. Okay. All right, there's curvature. Let's compute a plane, and then I'll eat more gummies, answer questions, and then we're done. I've used like half of this chalk stick already.
Only today?
Just today, yeah. Okay, let's do this. Find the equation of the plane. Containing the point it really doesn't matter. What did I pick? 1, 2, 1. And the line given by parametric equations, -1 plus t, negative t, and then 3 plus 2t. Okay. Let's see. I have a point and a line, and I want to find the equation of the plane containing them. So I think back and I remember that in order to find the equation of any plane ever, what do? I need a point on that plane, which we already have, and I need a normal vector. How do I find a normal vector in this scenario? We've got our line, and we've got this point. Typically, a good strategy for finding a normal vector is to take the cross product of two vectors in the plane. So one thing we could do is I could take a direction vector for the line, and then using this point, I could draw a vector like this, and then take the cross product of those. And that vector, that'll be the normal vector that I'm looking for. All right, so a direction vector for the line let's see, I can get that by picking off the coefficients in front of t here. So this would be like 1, -1, 2. That would be this vector. And then how could I get this vector? I'll take my point 1, 2, 1 and subtract any point on this line. So for example, I could get a point on the line by plugging in t equals 0. That would spit out the point -1, 0, 3. Subtract those 2 points. And then, so another vector parallel to the plane would be the vector 1, 2, 1 minus whatever r of 0 is, which is the vector 1, 2, 1 minus, what did I say? -1, 0, 3. Which is the vector 1 minus -1 is 2, 2 minus 0 is also 2, and then 1 minus 3 is -2. And here, whoops, here and here, these are the two blue vectors that I drew. Oh, so to get the direction vector for the line, I picked off the coefficients in front of t, which in this case were 1, -1, and 2. And then if the point was on the line, there would be many planes kind of spiraling around the line. that you could find. That's correct. Nice. Okay, so let's cross these, and then we'll finally be done. So I'll let the normal vector be the cross product of the two blue things. 1, negative 1, 2, cross 2, 2, negative 2, which is going to be the vector 2 minus 4 is negative 2. 4 minus negative 2 is 6. And 2 minus negative 2 is 4. That'll be the normal vector. We've got a point that I erased, 1, 2, 1. So the equation is negative 2 times x minus 1 plus 6 times y minus 2 plus 4 times z minus 1 equals 0. Okay. Done. Yeah, thanks, Abhishek. Okay, I have more gummies to eat. I will answer questions until I finish my gummies, and then I will sign off for the night. Thanks, everyone, for tuning in.
Thanks, Jeff.
Yep.
I think I'm not, probably not doing it, but like, I would definitely. Okay. Bye, Jeff.
See ya. Yep. Also, I said this, but these videos will go up on the channel as regular videos. Yeah, if you want to rewatch, and I'll also, maybe not tonight, but I'll hyperlink all of the examples in the description. So if you want to see like, oh, I want to do the optimization problem or watch that, then I'll I'll link things. 3 people in person. Oh, 4. 4. Jessica left. If you want to do that, Elijah, that's fine with me. You can let me know. Yeah, I don't think the Bon Appetit crew would be proud of my dinner tonight, which was gummies. Do I have a list of conceptual questions? No. I can try to think of more for tomorrow. When can you call me Professor Breen? You can call me that now if you want, but you don't need to. Hopefully in a couple of years. But even then, you can just call me Joe. All right. I need to go home. I'll sign off for now. Nice. Thanks, Elijah. Okay, goodbye, everyone. Until tomorrow. Okay.